Welcome to lecture number 12 of the course. So, in this lecture we will continue looking at the remaining types of analysis, structural analysis. So, in the previous two lecture we have looked at elastic first order analysis for which is valid for small displacement, then we have looked at elastic critical load analysis and inelastic critical load analysis. So, let us continue from there. So, in this lecture we will be talking about this remaining types of structural analysis. Okay. So, elastic first order is done, elastic critical load is done, inelastic critical load analysis is done. So, we will talk about elastic second order or also called simplified P delta analysis. So, in this analysis what we do, the force deformation response of the structural component or accent deformation is considered to be linear, okay, and equilibrium is considered in the deformed position. So, RS relationships are nonlinear. Recall what is R? The vector of external forces, and what is S? The vector of internal forces in the members, okay. And displacements are assumed to be vanishingly small for compatibility. That means, the VR relationships are linear. What do I mean by that? V means the deformations, okay, vector of deformations, and R is a vector of displacements at the structure level. Okay. So, there is only one source of nonlinearity, that is the nonlinear RS relationship due to equilibrium in the deformed position. Okay. So, again I will take the help of this same example. Okay. So, when I consider the equilibrium in the undeformed configuration, if I apply a horizontal load H, then the force in the spring is going to be H in the undeformed configuration. This load is P, the reaction is also P, as simple as that. When I consider the equilibrium in the deformed position, that means it goes by an the displacement is delta or by an angle theta. Okay. So, then this force is K into delta, as we have seen in the previous lecture, even in the lecture before. Okay. So, what is the reaction here? The reaction here, this is K into delta acting to the left, the H is acting to the right. So, if I show the reaction to the right, then this is K delta minus H. Okay. Now, we consider the equilibrium of this free body diagram. So, if I take moment about point A, then I can write K delta into the height H, which is producing a counterclockwise moment, is equal to P into delta, which is a clockwise moment, plus H into H, which is also a clockwise moment. So, K delta H is equal to P delta plus H into H. Okay. So, from here I can express the lateral load capital H is equal to K minus P by H into delta. Okay. So, what is this relationship telling me? This is a relation between the applied lateral load H and the displacement delta. Okay. So, that means what is this quantity? This quantity is nothing but the stiffness, and we call it the tangent stiffness KT. It is not the same elastic stiffness of the spring K, it has been reduced by P by H. What is P? Is the axial load applied on the column, and what is H? Is the height of the column. So, this P by H, this term is called the geometric stiffness. So, if I plot H versus delta, so H versus delta, if I do a elastic first order analysis, then this is the force versus displacement and the slope is the elastic stiffness K. When I do an elastic second order or simplified P delta analysis, this is also called simplified P delta analysis, then what is the stiffness? This is the stiffness. Okay. So, that is called KT, which is K minus P by H. So, that means this elastic first order stiffness is reduced by this stiffness, which I am plotting in the downward side. Okay. So, this is called the geometric stiffness and it is negative. Okay. So, H is equal to this. Now, what I want to do, I want to also look at the vertical load versus displacement. So, just like I am looking at the horizontal load versus displacement, I want to also look at the vertical load versus displacement. For that, what I want to do, I am considering or expressing the lateral load H as a factor multiplied by the gravity load P. So, H is equal to alpha into P. So, then from here from here I can write down this equation. How do I do that? So, from here I will write k into delta into h is equal to p into delta plus h is equal to alpha into p into h. So, from here you solve for p, okay, and then I want to normalize that p because I want to express it as a fraction of the critical load. What is the critical load? The critical load for this problem, if you recall, we have done in the previous class, PCR is equal to simply k into h, okay, where h is the height. So, I divide this p by PCR, then what you get is this equation. What you get is this equation, and I am also expressing all the delta by in a normalized form. So, delta by h. So, in the numerator you have delta by h, in the denominator also you have delta by h plus alpha. Okay. What is alpha? Is the fraction of the gravity load that is applied horizontally. So, this expression is fully dimensionless. Okay. Now, let me first concentrate on the left hand side figure. What I am showing is the h versus delta response, which I showed in the previous slide, the same thing, this one, but for different levels of axial force. And how I am doing that? I am saying the P, the applied axial force, is a certain factor beta times the critical load. Okay. What is the critical load? K into h. So, if I apply beta into k into h, okay, and if I plot the lateral force h versus the horizontal displacement delta, okay, note that I am normalizing this h by p critical and the displacement by little h. So, if I do a first order analysis, no matter whether the gravity load is present or not, this is going to be a straight line with the stiffness that is corresponding to elastic stiffness. Okay. But I have normalized, so the value will be basically unity. Okay. That is the reason it goes to 0.5 and this goes to 0.5. Now, imagine that I have applied gravity load which is 40% of the critical load. That means, I have applied 0.4 kH. So, what will happen? The stiffness will reduce, okay, because of the geometric stiffness. So, then this is the result. The force versus displacement relationship is linear, lateral load versus displacement is linear, but with a reduced stiffness because of the geometric stiffness. Now, if I increase the load, 80% of the critical load is now applied, then you see the stiffness is reduced further. When I apply 100% of the critical load, what is the stiffness or what is the load displacement plot? Well, the stiffness becomes 0, okay, because geometric stiffness is equal to the k. Okay. So, then it is going to be like this. So, then it is in critical condition, okay, or it has reached the bifurcation point. Okay. So, the take away from this is that the gravity load cannot be ignored and we must consider the P delta effect. As you can see, the stiffness is significantly reduced depending on the amount of gravity load that is applied on the structure. Okay. Now, let us switch gear and look at the vertical load versus the displacement with some horizontal load. That means, I am now plotting this equation. I am now plotting this equation. P by PCR is delta by h divided by delta by h plus alpha for various values of alpha. What do we see? When alpha is equal to 0, that means there are no lateral load, we just have the vertical load, right. Then we get bifurcation of equilibrium, which is this, the Euler critical load. Okay. It is not for Euler, I mean we cannot say Euler, because Euler critical load is basically considered for a pin column, okay, but this is the critical load. Okay. So, P by PCR is equal to 1 when there is no alpha. Now, if I introduce some lateral load, so alpha is only 5% of the gravity load, then what happens? As I keep on increasing the vertical force, okay, as I keep on increasing the vertical force, the horizontal displacement increases, okay, and the relationship is non-linear. If I keep increasing the alpha, so let us say from 0.05 to 0.1, then this is how it goes, okay, even further increase and so on. So, these are like asymptotically approaching the critical load, but there is a catch here. So, this analysis is not valid in this range, although I am showing it, Okay? This is not valid in this range. Can you think why it is not valid? Because if you look at my horizontal axis displacement delta by h, I am going up to 0.5. That means, the horizontal displacement is 50% of the height of the column. So, which is a large displacement. If the displacement is large, we got to consider the nonlinear compatibility, which I have not considered in this, because we are doing elastic second order simplified P delta analysis. So, therefore, this portion is not valid. I will show when we go for large displacement analysis, then how this change. Okay. So, the takeaway from this particular slide is that we need to consider the P delta effect when the gravity load is significant, because the stiffness is reduced due to the geometric stiffness. Okay. Now, let us look at inelastic first order analysis. So, when I say first order analysis, that means the equilibrium is undeformed configuration, the compatibility, for compatibility the displacements are assumed to be vanishingly small. That means linear VR relationship, linear RS relationship. But I am saying inelastic, that means the material behavior is nonlinear. So, that means the action deformation or the SV relationships are nonlinear, then we call it inelastic first order analysis. Okay. Where is the result for inelastic first order analysis? With reference to this figure. So, imagine that I am pushing it with this lateral load, okay, and then plastic hinges are forming at the ends of the beams, okay, at the ends of the beams and at the base of the column. So, then it forms a mechanism, is not it? So, then I can show the lateral load versus delta relationship is something like this, This asymptotically approaches the plastic limit load. What is the plastic limit load? Is the load that you would get if you do a plastic analysis. That means, you just consider the plastic hinges, okay, and do a plastic analysis to get the plastic collapse load. So, this is the plastic limit load, where I am saying that there is no gravity load, I am just considering the lateral load, okay, because if there is gravity load, we got to consider the P delta effect. So, this is the inelastic first order analysis. Okay. Now, if the P delta effect is negligibly small, then only this analysis produces an excellent representation of simple elastoplastic behavior and failure through mechanism formation or the plastic limit load, provided the P delta effect is small. If the gravity load is significant, you cannot do this analysis. Then what you need to do? You need to do inelastic second order P delta analysis. What is inelastic second order P delta analysis? So, material behavior is nonlinear as before. Equilibrium is now considered in the deformed position, or RS relationships are nonlinear. For compatibility, displacements are still assumed to be vanishingly small, hence VR relationships are linear. This produces excellent result for most structural engineering problems. Okay. Now, let us talk about elastic large displacement analysis. So, elastic large displacement, when I say elastic, that means material behavior is assumed to be linear elastic. So, action deformation relationships are linear, and equilibrium is considered in the deformed position, that means nonlinear RS relationship. Recall from lecture number 10 what I mean by nonlinear RS relationship. Go to the OpenSys example where I have applied a gravity load and a horizontal load, and when I increase the loads proportionately, the force in the spring does not increase proportionately, right. So, that is what I mean by this. Okay. Displacements are assumed to be now finite. They are not vanishingly small, but finite for compatibility. That means, I will be now considering nonlinear VR relationship. So, this produces excellent representation of the P delta effect, okay, and we can capture several modes of nonlinear elastic behavior. Okay. What are those? We can capture what is called bifurcation, which I have talked about. That means, system following an alternative path in post critical state, that means in post buckling. Okay. I can also capture gradually increasing nonlinearity, which can lead to elastic instability at a limit point. What I mean by that, I will explain through example. We can also capture increasing stiffness either from onset of loading, just after I start loading the stiffness increases, or following a gradual softening. All these things can be captured through elastic large displacement analysis. So, what is the example? So, with reference to this figure, so the elastic large displacement analysis can go here, and this is the bifurcation. From here, this is the post buckling path, okay? Or it can go like that and reach an elastic stability limit, okay, where there is lateral force. So, alpha is not equal to 0, it can go to elastic stability limit. Then there are problems where it can stiffen, not in this case, or in this case also it may happen depending on several things, okay. So, it can stiffen, right. So, let us look at example, simpler example where we can see all of these features. So, elastic large displacement analysis, again I will be taking this simple toy problem, okay. Recall when we displaced earlier, what was this? This delta was simply theta into h, right. But now, since this delta is finite and not vanishingly small for compatibility, what I will do? I will write delta is equal to h into sin theta. So, this is my h, because it is a rigid rod, the length was h. After I have rotated, the length remains the same h. So, this component is h into sin theta, whereas this component is h into cos theta. Okay. So, this force is same as before, k into delta, but delta is now h into sin theta, and the applied horizontal force is alpha times p, okay. And for equilibrium, this is k delta minus alpha p, and for vertical equilibrium, this is p, okay. Now, same as before, I take moment about this point, then this is the equation I get, okay, simply by taking moment about this point. From this, I can calculate what is the value of p, which is kh cos theta divided by 1 plus alpha cot theta. Okay. I can also determine from this equation capital H and express it in terms of the applied force P. Okay. So, if alpha is equal to 0, that means there is no lateral load applied, then what we get is P is equal to kh cos theta. Okay. So, if theta is small, then cos theta is equal to 1. So, P is equal to kh, that is the critical load we established earlier. But for large theta, what do we get? P is equal to kh cos theta, right. So, as theta increases, cos theta value reduces. So, that means this is less than kh. Okay. So, how does it look like? If I plot the vertical axis is my load normalized by kh, okay, and the horizontal axis is the displacement delta, again normalized by the height h, then this post buckling path is the blue one, is going like this, okay, for delta to the right, and then it can go in the left also. So, this is the unstable equilibrium in the post buckling when we consider large displacement, right. Now, let us consider alpha is not equal to 0, that means there is some lateral load. Okay. So, what will happen? If you have a lateral load, there will be displacement in the lateral direction right from the beginning, and now if you keep on increasing the vertical load, what happens? Then I can plot this equation. Okay. So, if I plot this equation P by kh with delta by h, then this is how it goes for different values of alpha. So, this green one is alpha is equal to 0.05, then this red is alpha is equal to 0.1, this is 0.15. Now, if you recall earlier when I showed this curve, when I did a simplified P delta analysis, this was going like that, and I said these are not valid. As you can see, these are going down. Okay. What is the peak value? If I join the peak, this is the trace of the limit point. Okay. This is called the trace of the limit point. Okay. We have reached the peak value, right. Okay. So, if I look at the H horizontal force versus delta relationship, where I am applying certain percentage of the critical load, which is kh from the simplified P delta analysis. Okay. So, if I express this P as some factor beta times kh and plot the lateral force versus displacement when there is no load or there is load, but you are doing a first order elastic analysis, then this is the lateral force versus displacement relationship. But imagine that there is gravity load P. Okay. If you do a simplified P delta analysis or a second order analysis, then the result is the dashed line here. This is the result for a simplified P delta analysis for 40% of the critical load as the applied gravity load. Okay. If you do a large displacement analysis, then green is the result. So, this solid line is the result for beta is equal to 0.4. For beta is equal to 0.8, the departure is like that. This is simplified P delta and this is the large displacement analysis. What is the take away from here? What is the horizontal axis? Delta by h, lateral displacement divided by the height. What does it mean? For a building, the lateral displacement of a floor divided by height is nothing but the story drift. Okay. So, when I look at 0.1 story drift means 10%, which is a large story drift. See, up to 10% or even slightly larger, what do we see? We do not see any difference between the dashed line and the solid line, meaning that the large displacement and the simplified P delta analysis both giving me the same result up to 0.1, okay, or even more. And 0.1 means 10% story drift is a really large drift. Okay. So, the takeaway is for most of the structural engineering problem, especially in the field of earthquake analysis and design, we are okay to consider simplified P delta analysis, but most, not always. I shall show you exceptions. And so, what I was mentioning in the previous slide, if I now look at the vertical force versus the displacement, okay. So, if I do a simplified P delta analysis or elastic critical load analysis, so this is my Euler critical load. Okay. So, for alpha is equal to 0, there are no lateral force, right. If you have no lateral force, but you do a large displacement analysis, then this is the result which I explained in the previous slide. Okay. If you now have different lateral loads, okay, so the result goes like so. Okay. And previously what we got for second order P delta analysis, it was going like that. It was going like that. Okay. So, that is why I mentioned that this part of the curves are not valid, because you need to consider the nonlinear compatibility. Okay. So, one more time, the takeaway is the P delta effect cannot be ignored, but we may be fine by doing a simplified P delta analysis or a second order P delta analysis for most of the structural engineering problem. Okay. So, some remarks: first order analysis can be erroneous if large gravity loads are present. I have emphasized it several times. For delta by h up to 0.1, no significant difference between P delta and large displacement analysis, and this is what I mentioned, that it is basically 10% story drift. Okay. So, for buildings under gravity and lateral load, it is rarely necessary to consider a true large displacement analysis. Okay. Then the question is, when do we need to consider the large displacement analysis? Okay. For example, consider two members, okay, connected by 3 hinges as shown, right. Now, if I am applying a load P here, okay, so let us say I keep on increasing the load, okay, in a manner I am actually applying displacement and measuring the reaction force P. Okay. So, then what will happen? Well, this will deform symmetrically as shown here by the blue, okay. And then if you keep on loading it further, that means increasing the displacement, eventually it will become horizontal, right, and then it will go to the other direction. So, what will be the load versus deflection behavior for this case? If you perform a large displacement analysis, that means you consider the equilibrium in the deformed configuration, you consider the displacement to be finite and take the nonlinear VR relationship, then you will be getting a force versus displacement relationship like this. Let me explain this. So, if you keep on increasing the load, okay, from 0, then what happens? You will move along this path and reach a maximum load which is called a limit point at point B, okay. So, which is shown here by this blue dashed line, right. This is the maximum load. Now, after that, if you keep on increasing the displacement, what will happen? The load will reduce, right, and eventually come to point C, where you have deflection, but the load is 0, which corresponds to this configuration, right. And then if you keep on increasing the displacement, the load will actually reverse the direction. It will be negative and it will go like this and come to the minimum load at point D, which is basically this configuration. Now, note that B and D are basically mirror image, these two configuration, right. And then, so here the load is in the opposite direction, negative. Now, if you keep pushing it further, then what will happen? The load will eventually come to 0 load. So, that is configuration E, and E and A means where there was no load, we just started to apply the load in a displacement controlled manner, right. So, A and E are mirror image of each other, and then after this point, if you keep pushing further, the load will increase significantly and it will keep going like that. So, if you perform a large displacement analysis, then you can capture this complete force displacement relationship, right. So, this is kind of a toy example. Where does it happen in reality? Well, if you have shallow arches or shallow spherical caps where the rise to span ratio is basically small, okay, rise to span ratio is small, then you can get what is called limit load buckling or limit load instability. So, basically you reach a limit point, right, and this is not a bifurcation buckling, right. So, for this kind of structure you can get that. Now, on the other hand, imagine that this height is increased keeping the span same, or we are talking about large rise to span ratio. So, you get a situation like this. Now, if you keep on increasing the load, what can happen? These individual members can actually buckle. So, you end up getting a bifurcation buckling, which in this case is asymmetric, okay. And where it can happen? It can happen in spherical caps and arches with large rise to span ratio as shown here. So, the force displacement relationship is going to be like this, and then all of a sudden there is a bifurcation of equilibrium, okay. Later on in the course, when we talk about nonlinear static analysis, I will show you that if you do a load control test, okay, then it will go through like this. So, you come to point B, that means you keep on increasing the load, okay, you are not controlling displacement. So, after point B, it will directly go here horizontally. So, that is called a snap through problem. But if you want to get this behavior, then you have to do a displacement control analysis or a test, okay. So, this is one example of large displacement analysis or situations where you have to perform large displacement analysis, okay. Another example of elastic large displacement analysis, when do we need to do it? Let us say when we want to consider the catenary effect. For example, I now start with this configuration, two rods which are pinned. In a linear structural analysis class, we will call that this structure is unstable. You have got pin, you apply slightest disturbance, slightest load, this is not going to take any load, okay. But if I consider, let us say, if I consider equilibrium in the deformed configuration, is that enough? No, because let us say this point moves here and I consider the equilibrium in the deformed configuration. It is not enough unless we consider the finite, the displacement is finite and the VR relationships are nonlinear, okay. So, if you recall in the, I think lecture number 10, we talked about a problem like this. So, you have a bar like this and then I am rotating this bar, okay, and in a manner that this point is not allowed to move up and down, it is basically going like that. It is basically going like that. And I did an example in OpenSys also and showed you, if you recall, the relationship between the deformation and the R is something like this, the nonlinear VR relationship. When R is small, there is no deformation. When R increases, then the deformation increases like this. And also the force that it can take, this force versus this displacement relationship is also like that. Okay. So, for this case, how can we capture this behavior? Well, we have to perform a large displacement analysis where we have to consider the nonlinear VR relationship, deformation of each bar using Pythagoras theorem. This length is square root of L square plus R square, where R is this displacement, minus L is the original length, and then consider the equilibrium in the deformed position. Then you will get this kind of force displacement behavior. So, this is called catenary effect. Where do we consider catenary effect, or where do we need to consider catenary effect? Where you have cables, let us say suspension bridge cables, cable state bridge cable, the cables in transmission line systems. Okay. So, where you have large displacement, right, and it causes a catenary effect, then you have to go for elastic large displacement analysis. Lastly, inelastic large displacement analysis. So, it considers all sources of nonlinearity. Material behavior is nonlinear, the equilibrium is in the deformed configuration, that means nonlinear RS relationship. Displacements are also finite for compatibility, that means nonlinear VR relationship. When do we use this? In civil engineering or in structural engineering. These are typically used, some example would be seismic or progressive collapse simulation of structural system. Let us say you have a building where a terrorist comes and put some explosive close to a column, right. The column is destroyed, then what will happen? Building, it is statically indeterminate system, right. So, the load will try to redistribute, okay, and then building may or may not collapse, but it may form a catenary action. Okay. So, it may collapse progressively. So, then in those cases, or let us say we are doing incremental dynamic analysis where a building is subjected to increasing level of seismic excitation, and we are interested in the fragility. Okay. We are trying to determine the probability of failure, right, considering the seismic hazard. Then we may have to consider we have to perform inelastic large displacement analysis. Okay. An example would be, I am showing you, this is seismic collapse simulation of a 10-story reinforced concrete frame building, which is subjected to bidirectional ground motion of increasing magnitude, okay, of increasing, I should say, the ground motion amplitude. Okay. Then here I am showing for a particular case at time t is equal to 1 second, the building is like this. At 27 seconds, the building is like this. The first floor is kind of coming down, which you are able to see. Okay. And then here, we are getting kind of a complete collapse, okay, at about 28 seconds. So, for this kind of analysis where the displacement is large, you need to consider both material nonlinearity as well as geometric nonlinearity, considering large displacement. Okay. So, with that, some final remarks. Geometric nonlinearity, it has two well defined causes, equilibrium and compatibility, and both are governed by clear mathematical rules. So, we can formulate things. On the other hand, for material nonlinearity, it can have many causes and many forms, although it stems from primarily nonlinear stress strain relationship, but in structural engineering it is very difficult to capture material nonlinearity through theory. So, our knowledge depends almost entirely on what we observe in experiments on actual structural components and systems in laboratory, and we tend to develop phenomenological model that can capture the material nonlinearity. So, that will be our next topic. After I finish the introduction, we will talk about, we will get into material nonlinearity, how we develop the different types of models that are good for, let us say, different types of material, starting from concrete, steel, and other materials. Okay. So, these are the references that I have used in this slide, and with that I will stop here today. Thank you, and we will see you in the next lecture. Thank you.